All right, so welcome to vector calculus. Let's begin by talking about what vector calculus is, to set the tone and to set the framework for the rest of the course. So you may have taken a bunch of calculus courses already. You may have had Calc 1, differentiation, Calc 2, integration, then a Drexel Calc 3 is infinite series. Who has taken that? Everybody, that's good, very important course. Calc 4, multivariable calculus, then maybe differential equations. That's a lot of calculus. And some of you may have even taken calculus in high school. That's a lot of calculus. So why one more course? Another course, vector calculus, a course that you should actually be very excited about because it will organize a lot of the knowledge that you've acquired in previous calculus classes, and it will actually give a lot of that knowledge that you already have new and maybe greater, maybe deeper meaning. You'll have a few aha moments, and it'll sort of give that knowledge purpose. So what previous calculus courses had in common is that they all dealt with, let's say, arithmetic objects. You dealt with functions like sines and cosines and polynomials, very specific functions removed from their physical meaning. That was true in every calculus course that you've taken. You worked with algebraic functions. Yes, there were applications, but that's actually how it was framed. It was something that you learned in relative abstraction, and then there was a physical application. And all of those objects were removed from their physical values. Right? You were never, when somebody asked you, when you were studying the derivative of the cosine function, you never asked, what does this cosine represent? What does this polynomial represent? What does this rational function represent? What does this exponent represent? You were just studying those algebraic objects. That's why I call that approach an arithmetic approach. Now, I mentioned occasionally you did applications. You did a falling body, half of you are physicists. You did areas under a curve, or maybe just areas. Great applications. And maybe one would say that application is the point of all of that. But if you think about how you did applications, those applications, the first thing you did was to convert whatever physical situations you were presented with back into functions, back into numbers, back into arithmetic. So the goal was to, as quickly as possible, forget about where the problem came from, convert it to this arithmetic space where you felt comfortable because that's where they taught you how to do calculus. Calculus was a matter of sines, taking derivatives of sines and cosines, exponential functions, logs, and so forth. So that was your comfort zone, as it should have been. And then you would just proceed in the arithmetic space. And you would get your specific answer, either a number or a specific function, and you would then interpret it, or maybe reinterpret it in the physical application. You would say, oh, the answer is 5. That means it took the body 5 seconds to fall from a certain height. Oh, the answer is 37. Well, that means that the volume of this shape is 37 meters cubed. So at the very last moment, you would go back and interpret your numerical answer, sometimes analytical answer like 2 sine x. Oh, well, that means that it looks like this. You would just go ahead and reinterpret it in the framework of the original problem. There's really nothing wrong with that, except there are lots of things wrong with that. And that's what this course will help you fix. Here is what's wrong with that. I don't know what order to list things. You know, it's not that it was the wrong approach, but you definitely need this new approach that you will learn in this class. So, well, let me begin by saying that, you know, sometimes when you get a specific answer, you might miss the bigger conclusion, the deeper conclusion. You might get that the answer is 3, and then all it is just the answer 3 for a specific problem. But we can do better than that as human beings. And as scientists, we always strive to do better than that. You know, you could work with right triangles your whole life and calculate the length of the two sides and the length of the hypotenuse, and not ever realize that the square of the hypotenuse equals the sum of the squares of the other sides, right? If that's what might happen when you work with specific numbers, you might miss a fundamental fact when you focus on the numbers a little bit too much. So that's one example. What we want to do is learn insightful things. We're not robots. The greatest advantage that humans have over computers is that they see the general facts. They see the generalizations. They see the abstractions. That's sort of the power of logic and the power of the human mind. So I feel that we haven't, in our earlier calculus classes, we haven't fully taken advantage of that because we focused too much on the technique, on the nitty-gritty things removed from the physical reality. That's number one. Number two, and that will really be sort of a similar point, we're not treating objects on their own terms. We're kind of working with their representations. We forget about what the objects are. And I guess I should mention at this point that what I'm sort of taking on as a battle is the overwhelming use of coordinate systems. Now, coordinate systems are great. They were given to us by René Descartes. They were really a watershed event in science. It was the moment where algebra and geometry came together, and once that happened, their development was greatly accelerated. And that ultimately led to the development of calculus. So it's a very, very important thing. And the subject that I love and have a whole series about, and actually a book, is tensor calculus. It's all about coordinate systems. So I'm not saying that coordinate systems are bad. What I'm saying is that over-reliance on coordinate systems can make you miss the essential properties of objects. They can make you miss the essence of objects. And that's what I'm hoping to bring back in this course, the focus on the essence of objects. So what happens when you have a coordinate system? So what I'm arguing against is over-reliance on coordinate systems. So my number one goal in this course is to wean you off coordinate systems. And you'll see exactly what I mean by that. So what usually happens? Let me just give you, an example. I guess it's an example. You're presented with some kind of a problem, and then you immediately impose a coordinate system, usually a Cartesian coordinate system, probably 99% of the time. It's usually, you might not even say that I'm using a Cartesian coordinate system. It will be implied that, of course, there is a regular grid, and of course, I'm referring everything to the regular grid. And of course, now I have numbers instead of objects, and now I'm comfortable because I know how to work with them. So it's this focus on representing objects by their coordinates that make us forget what objects are. And we shouldn't forget what objects are. And when we don't forget what objects are and treat objects on their own terms, that's when we begin to discover more fundamental things. And that's what vector calculus will be about. So now let me define how I see vector calculus. So I see vector calculus as the study of physical objects, maybe geometric objects, but actual objects. We'll study actual curves, actual surfaces. We'll start by studying actual straight lines. And then maybe we'll study physical objects with mass and so forth. And we'll study those objects directly. So we won't think of a vector, which I'm about to talk about vectors, as a set of three numbers. We'll think of it as a vector. And you will see that you can do a lot with some very important limitations, but still a lot, by treating objects on their own terms. When we'll say a curve, we'll mean a curve. We won't mean its function representation or its numerical representation. We'll work with objects directly. And what you will notice is that when you work with objects directly, you're beginning to see the world in a very insightful way. You'll begin to see objects and their properties and their characteristics and their character and all of that. So that's what vector calculus will be. It will be a rehashing of everything you've already learned, but in a very natural setting where the objects are being treated for what they are directly. And half of you are physicists, and that should appeal to you because you're studying the physical world. So it will be refreshing for you to see that you can study the physical world directly. So goal number one is to wean you off your overwhelming dependence on coordinate systems. I want you to, for the time being, forget about the coordinate systems, and then we'll bring them back and rebuild our understanding and use of coordinate systems in the right setting. Okay, so that's vector calculus.